Welcome to Math 106, Chapter 3.3, Part 2, where we talk about related rates. Now, at the end of this video, there is going to be a follow-up video just going over a few more related rate examples that you're going to be seeing on your homework. So definitely stay tuned for those on our next video. Now, related rates are do a lot with implicit differentiation. That is why they get paired together. Because in our class from our previous video, we learned how to derive when there was multiple variables. Now, related rates, there's going to be some sort of time aspect, which this is going to enter in a third variable. Now, it might not always be explicitly seen in the equation, but usually in some sort of context, they're going to ask for this time relation, in which case you're not going to notice that there is a third variable present. It is hidden. It's just going to represent some sort of a time application. So it says, in some applications where x and y are related by an equation, both variables are functions of a third variable, t, which may represent time. Often formulas for x and y or functions of time are not known. When we differentiate such an equation with respect to t, we derive a relationship between the average rate of change, dy dt, and dx dt. We say that these derivatives are related rates. The equations relating the rates may be used to find one of the rates when the other is known. So when we go to solve, right, typically last time we solved for dy dt, but in our case, you might be asked to solve for dx dt if we already know dy dt, and vice versa. It is all depending on what is given and what is not. So let's take a look at example 4. It says, suppose that that x and y are both differentiable functions of t. So they both have some factor of t and are related by the equation x squared plus y squared is equal to 36. At no point in time do you see the t variable here, but they do say in our example that they are differentiable from t. So if we solve your equation resulting in dy dt with respect to t, let's go ahead and take a look at what that might be. So very similar to our last video, our last lecture, right? We said, okay, well, let's break this up, right? Let's step 1, derive the x term. Now, very similar to last time, right? When we were deriving in a specific variable, we also said to add something to it. Now, we typically added this to dy, all right, to your y term. But when it comes to deriving your x term, we're going to derive and then add dx dt. So if we look at x squared plus 5 y squared is equal to 36. When we derive your x, we should get 2x. When you finish deriving, we're going to add dx dt. Step 2, let's derive your y term and add, instead of dy dx, we're going to be adding dy dt, right? Because each of our variables needs to have some sort of the t aspect, in our case, perhaps time. So if we have 2x dx dt plus 10 y to the first dy dt. So kind of taking them in parts. Now your last remaining part, so if I throw this over here and actually, let me just go ahead and copy. Throw it over here, paste. We now can go ahead and derive your constant, which because it's a constant, right, there's no variable to it, it's just going to be 0. Now, it does ask us to solve for dy dt. That means that this one needs to be isolated. So let's go ahead and isolate that particular term. So we can go ahead and bring your 2x dx dt over to the other side. So subtracting it over to the other side, we still have dy dt here that we're solving for. Now let's go ahead and isolate it. So divide and simplify. So you have dy dt, dx dt over here. Let's see, we have negative x over 5y. So when we pick these apart, dx dt is the rate at which x is changing with respect to t. And maybe t is time. So maybe it's changing at a rate of some sort of time. Whereas y is the rate, and I'm just going to throw this over here, is the rate at which your y is now changing with respect to t, or perhaps time. So that if everything is given, they're telling us what x is, what y is, and what dx dt is, we can solve and calculate dy dt. So let's see if you can go ahead and substitute those in. So if we have all of this right here, one more time, I'm going to grab this so I don't have to constantly write it. There we go. So if we are trying to find dy dt, but we know that x is equal to 4, y is equal to 2, and dx dt is equal to 5, we can go ahead and work all of those in. So we can get negative 4 over 5 times 2 times 5. And if you want, you can multiply your 5 up here because it was up in your numerator. But notice that you have 5 up top and on the bottom. And when we simplify, we should just get a negative 2. Now, what this means is that, again, your rate, your y is changing. So the rate at which y is changing in terms of t, perhaps it's time, is decreasing by 2. I'm going to say decreasing because it is negative here. That negative is just meaning that we are falling, we are decreasing, we are going down by a measure of 2. And we can see that here over that particular point for 2, right? We were given that coordinate. We said x is 4, y is 2, and dx dt is equal to 5, right? And you can clearly see that your y is decreasing by a measure of 2. So perhaps 2 units, I guess 2 units. So let's try again with example 5. It says, suppose that X 1,000 units of commodity can be sold weekly when the price is P dollar units or per units, and that X and P satisfy the demand of the equation. P plus 2X plus XP is equal to 38. How fast are weekly sales changing at a time when X is 4, P is 6, and the price is falling at a rate of 0.4 dollars or 40 cents per week? So what is given, right? Can we pick out what we now know? Well, what is it? What is X? Let's start with there. Not X as in, okay, I know it's 4. I want to know what is the context of X. Well, it says X is thousands of units of a commodity. So this is units sold weekly, and it's in thousands. So it's not just, oh, it's 4, right? This is actually 4 thousands, and it can be weekly sold. So what is P? The context of P. P is price. We do know we have a T here, and we want to know your time, right? So T is time. We also know that X is equal to 4, or 4,000 in the context of our problem. P is equal to 6. Now we're also given this 40 cents, right? Well, what is the 40 cents really talking about, right? Well, it says that 40 cents is the price is falling at a rate. Price is falling at a rate of 40 cents per week. So do we, in other words, have dp dt or dx dt if the price is falling at a rate of 40 cents? Well, it would be dp dt. Now it's 40 cents, but keep in mind the key word here is that it's falling. So we now have some sort of negative measure. Therefore, what are we trying to find? Well, we want to figure out how fast are the weekly sales changing. We said weekly sales is that unit for X, weekly sales at some sort of a time function. So let's take your function here, P plus 2X plus XP is equal to 38. I'm sorry, it's not there we go. So let's go ahead and see if you can derive. So deriving each term slowly, deriving P, it should just be 1, but what do we get to add to it? Well, we're going to add dp dt, right? So it's 1, right? That is your derivative of P. It's just 1. And then when you finish deriving, we have to add dp dt plus, let's go ahead and derive X, 2. And what do we have to add? This time we add dx dt. Now we do have the product rule here, which I'm going to just go back over here and grab one of my product rules so I don't have to restate it all. And maybe I move that over here. So we have X, the derivative of X is 1. P, the derivative of P is 1. And we now need to add dx dp, dx dt, and dx, nope, dp dt. It's hard when they all sound alike. So when we go to put it together, right, we should get plus 1 dx dt times your P, that's G, right, of X, plus your F of X, which is just X, times 1 dp dt. There we go. And on the other side, deriving, we get just 0. So we are trying to solve for what variable? Well, we said we are trying to solve for dx dt. So let's get these to one side. That means everything else needs to come over. So you have 2 plus p, and these both have dx dt. And on the other side, we should have subtracted your 1. We should have subtracted your X. And both of these have dp dt, dp dt. There we go. Now let's go ahead and solve for dx dt over on the other side by factoring it out. We should get 2 plus p here. And on the other side, you don't have to factor it out by any means, but if you'd like to, that's something that I would say try to simplify here. I would take out a negative and take out my dp dt so that you could have just x plus 1 over here. Let's go ahead and divide. So we should get dx dt is equal to negative dp dt x plus 1 over 2 plus p, or p plus 2. So that is your dx dt. So now that we have dx dt solved for, we now need to figure out at what rate is it changing? How fast are weekly sales changing at that particular time? So we know that x is 4, p is 6, and dp dt we said is negative 0.40. So when we go to plug that all in, we should get negative, and this is a negative 0.40. X is 4 plus 1 over 6 plus 2. So we should get 0.40 times 5 over 8. Now let's go ahead and plug that into our calculators, which if I have mine, should get 0.4 times 5 divided by 8. So we should get 25. Or 0.25, I should say. Now let's take a look at what that actually means. So keep in mind, we are looking for the how fast weekly sales are changing at a particular time. So we could say something that along the lines that the units sold weekly is changing or rising. And we can say it's rising because it did not come out as negative. We are going up. So it's rising by 0.25 thousand commodities per week. That is what our answer is telling us about. It's how fast your commodities are changing for the week. And we know that commodity is actually going to be in our thousands. So we are changing by 0.25 thousand commodities each week. So that is kind of the end of the video. Our next video, we'll just go over a few more related rates cases that might come up for your homework. So if you need it, please go to our next video. But suggestions for solving for related rates problem: first, draw a picture if possible. Ours doesn't really have much context to your picture here, but in the future, perhaps the ones that we'll see in our next video, you might need to draw a picture. Assign letters to quantities that vary and identify one variable, say t, on which the other variables depend. Find an equation that relates the variables to one another. Differentiate the equation with respect to the independent variable t. Use the chain rule whenever possible. Substitute all specified values for your variable in their derivatives, and then solve for the derivative that gives our unknown rate. And again, we can kind of see, I keep forgetting that there is a picture over here. We can see that the price is falling at a particular rate, right? Your price being this Y value. So it is falling. However, right, your X value is still going to continue to grow. It is rising, even if our price is falling.